Example 8.5, page 227. The launching mechanism of a toy gun consists of a spring of unknown spring constant. We have a toy gun where we have a spring inside with a unknown spring constant. K is unknown. When the spring is compressed, so initially we have the spring at the position B and we have a projectile. We have an object at the position B. We compress the second state. We compress the system to the position A. When the spring is compressed 0.12 meter, so we have a compression x equals to 0.12 meter. The gun, when fired vertically, is able to launch a 35-gram projectile to a maximum height of 20 meters above the position of the projectile before firing. So this gun is able to fire, okay, is able to fire a small object projectile of mass equals to 35 gram. So the mass of the ball, m of the ball, equals to 35 gram. This ball is launched to the maximum height at the point C equals to 20 meter between the point C and the position A, okay? Between A and C, we have 20 meter. Neglecting all resistive forces, we don't have friction, we don't have air resistance, determine the spring constant. Okay. So here we have a spring initially is at the position B, and we have a ball. This position is a equilibrium position where we don't have compression, we don't have expansion. Here we have x equals to 0. Okay. Now we compress the system to the position A, where we have x equals 0.12. Okay. At the position A, we have the ball at the position A, and we have a spring compressed with a distance x. At this point, we have the ball is at rest and the spring is at rest. Let's take the minimum level. We have the level of A, and the maximum position is the position C. We can draw here the x-axis and y-axis. Here we have the height equals to 0. Always, if you have many level A, B, C, like this case, you have to take the lowest position as x and y. Okay? Here we have y and x. You know the system consists of a spring and a ball. We have only two objects inside the system. The spring is massless. It doesn't have a mass. So we don't have a potential energy G, PEG, because we don't have MGH, M equals to O. We don't have, I'm talking about the spring. The spring doesn't have a potential energy. The spring doesn't have a kinetic energy, have mv square, okay? But the spring has a elastic potential energy, have kx square, okay? So now at this point about the spring, we have for the spring, we have a elastic potential energy, elastic equals to have kx square because we have a compression. Okay, this is about the spring. About the ball doesn't have a velocity, so we don't have a kinetic energy. Kinetic energy equals to O. Uh, the ball doesn't have a height because the height is limited as a point A. mgh, h equals to O. So potential energy at this position equals to O. But also, it's all about the ball. Let's say this position is a position, the system 1. Okay? In the system 1, we have the potential, elastic potential energy of the spring. We have no kinetic energy and we have no potential energy of the system. Okay, here we have system 1, so potential energy elastic or elastic potential energy 1, and the kinetic energy 1, potential energy 1. Now we launched, the ball of the system is launched from the point A, and the spring will push the ball up at the position B. When the system arrives to the position B, the ball will continue to move up to the point C, and the spring will stop at the position B again. Why? Because the ball is not attached to the spring. If the ball is attached to the spring, we will get a simple harmonic motion at this level. Okay? So the third case, when the system is launched, as you see here, the spring arrive to the equilibrium position. The spring will stop at this point, and the ball will continue, will be separated and continue with a new velocity VB at the position B. Okay, let's say what we have in this system. When the system is at this point, let's say we have system 2. Here, the spring is at rest. Let's talk about the spring. The spring is at rest, so we don't have a compression. In this case, the elastic potential energy, P E elastic equals to O. I'm talking about the system at the second state, 2. We don't have a elastic potential energy. Okay, it's all about the spring. Now let's talk about the ball. The ball at this point has a velocity, so we have kinetic energy. The ball at this point has a height equals to x. Okay, look here. We have a height here equals to x. So we have a gravitational potential energy. So for the ball, we have two things. We have the kinetic energy and we have the gravitational potential energy. Kinetic energy in the system 2 equals to have mvb square. I don't talk about the kinetic energy of the spring because the spring doesn't have a mass. And we have the gravitational potential energy of the ball. In the system 2, we have mg, and the height equals to x, because I am taking the reference as the position of A. Okay, that's all about this state. Let's talk about the third state, when the ball arrives to the highest point. At this point, the spring will stop at this point, at the equilibrium position, and the ball will continue to the highest point. Let's say here we have a new state, state 3. In this state, v doesn't have a velocity, is a maximum position. So the ball, the kinetic energy equals to O. Kinetic energy of state 3 equals to O. The ball has a height equals to 20 meter between A and C. Here we have 20 meter. So we have a gravitational potential energy of the ball at this point. So we have here a potential energy, gravitational potential energy at the state 3 equals to m of the ball times g times, let's say we have h. This one is h. And we don't have elastic kinetic energy because here elastic potential energy, because at this point the spring is not compressed and is not we don't have compression and elongation. So we can say the potential energy elastic of the state 3 equals to O. This is in details for each state. We have the potential, the kinetic energy, and the elastic potential energy. And now let's explain a very important point. How can we solve this kind of problems? In general, to solve this kind of problem, you have to know here we have a isolated system. Okay, you can use the general relation delta mechanical energy equals to delta kinetic energy plus delta potential energy, okay, equals to the work done by the friction. This is the general relation between the mechanical energy, kinetic energy, and potential energy, and the friction, the resistance of the motion if we have, okay? Now, in our case here, we don't have friction. We don't have a resistance of any resistance. So in this case, F equals to O. So delta mechanical energy equals to O. Mechanical energy final minus mechanical energy initial. Final and initial, it depends the positions. We can say 2 and 1, okay, equals to O. So mechanical energy 2 equals to mechanical energy 1. In this case, we have a conservation of mechanical energy. Here, we can take the position 1 and 2 as you like. For example, here we have system 1, system 2, and system 3. We can say, I mean by 1 and 2, we can take the mechanical energy of system 1 equals to 2. We can say the mechanical energy of system 1 equals to the mechanical energy of the system 3. We can also say the mechanical energy of the system 2 equals to the mechanical energy of the system 3. Okay, as you like. Let me write the three cases. Here we have system 1, 2, and 3. So mechanical energy of system 1 equals to the mechanical energy of system 2. Or we can say mechanical energy of system 2 equals to the mechanical energy of system 3, and mechanical energy between 1 and 3. We have a conservation of mechanical energy only in the case if we don't have friction. We don't have F. Let me take the first case. If we take, I need to calculate K anyway, K. If I take between 1 and 2, between 1 and 2, here we have a noun K, and here we have a noun V. So we get finally one equation with two unknowns, okay? I cannot calculate K. If I take the between 2 and 3, between these two positions, in the state 2, we have VB unknown, and in the state 3, we don't have unknown. Okay, but I don't need to calculate VB. I want to calculate K. So I have to take the first case into account. Let's take the third case between 1 and 3. In the case 1, we have K unknown. In the case 3, we don't have unknown. Okay, because the velocity of the point C equals to O. So it's better to take this state between 1 and 3. Mechanical energy 1 equals to mechanical energy 3. Mechanical energy equals to the kinetic energy plus potential energy. Okay, so here we have kinetic 1, potential energy G plus potential energy elastic. Okay, 1 and 1. And 3 here we have kinetic energy 3 plus potential energy, gravitational potential energy G, and potential energy elastic 3. We come here to the state 1. What we have? We don't have kinetic, we don't have potential, we have just elastic. So here we don't have potential, we don't have gravitational potential energy, we have just elastic, have kx squared, okay, equals the state, the third state. We don't have kinetic here, we don't have elastic, we have just gravitational potential energy mgh. So here we have mgh. mgh. Okay, I need to calculate the k. So k equals to 2 mgh divided by x squared equals to 2 times m equals 35 gram, 35 times 10 power minus 3 kilogram times h equals to 20 meter, and g equals to 10 divided by x square equals to 0.12 square. We get k equals to 9.953 Newton. Okay. Okay. Let's take part B. Part B, find the speed of the projectile as it moves through the equilibrium position of the spring as shown in the figure. As you see here, I want to calculate the speed as a position B, is the equilibrium position. Okay? Okay. We have K, we calculated K equals to 953 Newton per meter. I want to calculate VB at this position. You know, VB is at a height of x equals 0.12, okay? B. To calculate B, we can apply the same equation of conservation of mechanical energy between the state 1 and 2, or between state 2 and 3. It's the same result, okay? We can choose as we like. Here we can take between 1 and 2, and we can solve the problem. And second methods between 2 and 3 states. Here we have 3 states. Let's solve the problem with 2 methods. First of all, between 1 and 2, mechanical energy 1 equals to mechanical energy 2. In the case 1, we have just the elastic potential energy. We have K over 2 x squared. We have x and we have K, okay? And we don't have kinetic and we don't have gravitational potential energy. In the state 2, we have mgx and have mvb square. So here we have mgx plus m over 2 vb square. Why we have mgx? Because the ball at this position is at a height of x. Here we have x-axis. Here we have x-axis at this point. And the point B is at a height equals to x. So here we have K, we have X, we have M, we have G, we have X, we have M. We can calculate VB, okay? We have 953 divided by 2 times 0.12 square equals to M 35 times 10 minus 3 times 10 times x plus M times 10 minus 3 divided by 2 times VB square. We can calculate VB equals equals to 19.7 m per second. Okay, this is about the state 1 and 2. You can use the state 2 and 3, mechanical energy 2 equals to mechanical energy 3. In the case 2, we have mgx and have mvb square. So mgx plus have mvb square, and the last case we have mgh. Okay, we can calculate VB. You have M, M, and M. G equals to 10, X equals to 0.12 plus half VB square equals to 10 times H equals to 20. We calculate VB equals to 19.7 amp per second. Okay, so you can use any states between 1, 2, 1, 3, 2, 3 as you like. You will get the same result. It's the most important